Here we are for chapter 2 in Chem 100 on the topic of measurements and calculations. There we go. And this chapter constitutes the second chapter that will be covered in exam 1. Next time we meet, we'll cover chapter 3, and then we'll follow that up with a subsequent meeting and do a review of all 3 chapters before the following meeting, which will be the exam. By the way, if you, and most of you will, take the exam in Brightspace using Respondus Monitor Lockdown Browser, and you get into the exam and you experience a problem, you're locked into the exam until you finish it. So if you need to contact me, you need to use a different computer or your smartphone, and I will be zoomed in on that day based on the schedule, and I'll be able to hopefully help you through any problems you have. If you don't have a second computer and you don't have a smartphone, it'll be okay for you in the event you have a problem to call me on my cell phone, and my contact information is in the syllabus. It's in Brightspace too. But you won't be able to Zoom while you're in the exam, because Lockdown Browser prevents any other activities but taking the exam. But I will be here on that time, zoomed in, and I'll have my cell phone so you can contact me if you need. Okay, so let's get to chapter 2. There we go. We have just a few topics. So in the time allowed, I'll have plenty of time to expound and digress a little bit if necessary. So, in the sciences, and in our case, chemistry, it's necessary 9 times out of 10 to make some sort of measurement. Now, typically, if you're a non-scientist, you think of measurements as measuring the length of something, or maybe measuring the volume of something. Like when you're baking a cake, you're supposed to measure out some water or milk and measure out your dry ingredients. And it's not much different in the sciences, the measurement part. How we express the measurement is the difference. We are keenly aware of the fact that any measurement, a quantitative observation, requires that you express a magnitude of some type, a number. But the number alone doesn't tell you everything about that measurement. You need a unit of measurement. And by the way, quantitative observations mean that there's a number, quantity. Some observations that we make are qualitative. And that simply describes some quality that's not, that may be quantifiable, but we're not doing it right now. For instance, the color. We say the sky is blue. That's a qualitative expression of our observation. But if we make a measurement with an instrument that's properly calibrated, we can get a spectrum, multiple measurements of the sky. And since our eyes are perceiving blue, we may measure a peak of intensity at a wavelength of, say, 450 nanometers, which is a measure of wavelength. So there you have a number and a unit of measure. All right. So it's also helpful to try to develop an intuition about the magnitude of a measurement. In other words, when I say inch, most people in the United States understand instantly that an inch is about that big. If I say a foot, they know it's about that big. If I say a yard, they know it's about that big. Okay. If I say I traveled so many miles, you have an intuition about how far that is. Like it's 12.5 miles from this campus to my front door. And I have a feel for that. In the sciences, though, we don't use that English system or the imperial measurement system typically. Some corners of sciences still use the English system. In fact, the discipline from which I come, agriculture, farmers, older farmers, would still use the English system, and they would say the yield of that crop was so many pounds per acre, so many bushels per acre. But the world over speaks of the yield of a crop in terms of kilograms per hectare. Right? Now, the yield is the same in either case, but the expression of how much is different because of the units of measure. Okay, so back to the topic. These two parts must always be present when you make a measurement. There are times when numbers are derived from calculations, and those numbers are maybe unitless. Sometimes you do that, and in fact, you may make a measurement with an instrument that's designed to combine several measurements in the process and give you a dimensionless number, right? So I guess technically you could say that that is a dimensionless measurement. But in fact, the instrument is making measurements with units several times of different types and combining them before it gives you an answer. It's what's known as a black box. But for our purposes, we're going to stick to a number and a unit combined is a measurement. The unit tells us the scale. In other words, if I say, I'm going to go out and go for a walk, and I'm going to walk for a mile, get my exercise. I could just as easily say, for that same distance, I'm going to go out and walk 5,280 feet. Okay. I walk the same distance. It's just a different unit of measure. And notice the unit of measure, when it changes, the value, the number changes also. Now, some numbers are, in the sciences in particular, numbers and their units dictate that the numbers are huge, or in some cases, very, very small, microscopic, submicroscopic. And we want a convenient way to express those numbers so that we don't have to write out decimal point and 32 zeros, and then you get to non-zero numbers. And so we want a convenient way to express that. And one of those ways is called scientific notation. Now, the authors of your textbook, I believe, may, and if your textbook doesn't do this, then you may see it elsewhere. Sometimes they reference exponential notation. Exponential notation simply means that you have converted a number into a form that is a coefficient times a power of 10. So I could take 93 million, and that, by the way, is the distance in miles from the Earth, the average distance of miles from the Earth to the sun. All right, so if I take this number and I put it in exponential notation, I can choose any power of 10. So I can say the decimal points here, I can say 1, 2, 3. So I can say this times 93.000. That's the same as this number, right, in exponential notation. Scientific notation is a special case. In scientific notation, the rule is that the coefficient in the number must be between 1 and 10. In fact, it cannot be 10. If it gets to 10, that's another power of 10. Right? So if I take this number and write it in scientific notation, the decimal point moves 1, 2, 3, 4, 5, 6, 7 places to the left. That means the power of 10 is positive. Right? We have stored up 1 million, actually 1 billion, in that number. And what's left is the decimal point has moved to this place right here. And in the process, you've stored up that information in that power of 10. Now, one thing you should always get in the habit of doing is when you do a calculation, when you solve a problem, ask yourself, the last thing you ask yourself is, does this answer make sense? Okay, does this answer make sense? Well, the distance from the Earth to the sun is very large. So it makes sense that this would be a very large number. If we put a minus there, it'd be a very small number, and that wouldn't make sense. And then to check yourself, if you multiply 9.3 times whatever 10 to the 7th is, then you should get that number. Okay. That's scientific notation. And the example here is a very large number. So what happens if my scientific notation gives me a coefficient of 10? You still have to move the decimal point another place, and that makes it 1 times 10 raised another power. So it's got to be between, it's got to be, the coefficient has to be between 1 and less than 10. Okay. So if we had to move the decimal place to the right, we would be storing up negative powers of 10. And I think I've got an example here. This would move the decimal point to the left, right? We moved it from here to here. So we stored up 2 decimal places, which is 2 powers of 10, 10 squared. And what we have is left over is the coefficient is 3.45. How about this negative number, right? If we move the decimal point here, it's got to move to the right to make the coefficient be between 1 and 10. So we moved it 2 places to the right, and we were storing up negative powers of 10 doing that. Notice the coefficient's getting bigger, so the power of 10 has to get smaller. All right. Let's check this one out. Which of the following correctly expresses this number in scientific notation? So we have 788.2. Well, where's the decimal point? It's understood to be right here. Now, there are different types of decimal points in the sciences. One is understood, and all numbers have decimal points someplace. But hopefully it'll become obvious later that there's another type of decimal point called explicit. That's the one that the person who writes the number actually puts the decimal point in place. Now, when you have a number like this, you don't have to put the decimal point there. You have to put the decimal point when there are zeros involved. Okay, so this one has a decimal there, and if we move it 1, 2, 3, we've stored up 10 to the third power in that movement. And that leaves us with a 2 as our coefficient, which should be right there. Okay, here's another one. This one's not a large number. This is a very small number. 1, 2, 3, 4, and 4, 9, 6. Okay, the decimal point in this case is explicit. We have to put the decimal point there, otherwise we may think it's over here. Right? We have to put it there. We have to be specific, explicit in where the decimal point is located. And another thing that will be counted as wrong in any answer is if you have a decimal out here with zeros, and if you leave that 0 off, the answer is wrong. The problem with what I call orphaned decimal is that in the US system, our decimal points look like a point. They look like a period. If you put that number in a sentence, it may be mistaken for a period if you don't bracket it in. Now we know that that's a decimal point and not a period in a sentence. Okay, back to the conversion. We're going to have to move the decimal to the right, right? 1, 2, 3, 4, 5. So we have 4.96 as our coefficient, and we moved it 5 places to the right. We stored up negative powers of 10 by moving the decimal to the right. And it makes sense because this is a very small number times that number, and this is a very small number from which it was derived. Okay, so our answer is right there. Okay, this is, I guess, kind of a review. Quantitative observations always have 2 parts, as far as we're concerned: a number and a unit. For measurement's sake. Sometimes calculations, though, give us combinations of units. One thing you have to remember is when you're doing a calculation with 2 numbers that have units, you don't just operate on the numbers. You also operate on the units of measure. So if one number times another number gives you this value, but one of the numbers has the units of a joule, which is a unit of energy, and the other number has a unit of seconds, then joules times seconds is your unit of measure. Now, one other problem that had to be overcome in the modern era of sciences is if scientists are going to communicate with each other, they need to have a common language. Now, I don't just mean the prose language, like how do you write a letter to a peer that's working in the same area that you are. Well, in the beginning of the, throughout the Middle Ages, in fact, even into the modern era for a time, communication was by Latin, because most educated people were educated by the church and they learned Latin. So they all communicated in that common language, even though the vernacular for each one might be different, like the English for one, French for another, German for another. They all knew Latin, so they communicated with Latin. But when we come to talking about measurements and calculations and development of laws and theories, which I'll describe later, you need to have not only a common language there, but a common language of units of measure. When I write to a colleague and say a kilogram, they know exactly what I mean, because the kilogram has been standardized as a certain size, a mass. Okay, and that's our first fundamental unit in the international system. Right, that's French. Right? So in English, it's international system. These SI units are defined and agreed upon by a worldwide council. Mass, the standard of measurement for mass, is a kilogram. And a kilogram is represented by a cylinder that's made of an alloy of platinum and iridium. That makes it unreactive, right? It will not tarnish. So once you've established that mass, it will not change over time. But just to be careful, just to be sure, we take that cylinder and we put it inside a bell jar. You know what a bell jar is. And we fill it with argon and inert gas. And then we put another bell jar over it and fill that with the argon. So the ultimate standard is located in that double bell jar in a cave in France. And it's under high security. Now, there are duplicate cylinders that have been created, but there's only one original. And if you want to standardize your kilogram, you send it to them, send it to France, and they will compare it to their standard. And then they will tell you what the mass of your cylinder actually is. Now, it's a very expensive process, so it's not done very often. Usually, companies that are working in that area that are standardizing masses for manufacturing balances, for instance, they need to know exactly what their standard weights are in comparison to the original. Okay, length. The standard length in the SI system is the meter. And that's where we get the term metric system, is because of that. Originally, the meter was a subdivision of the distance from the equator to the North Pole on a longitude passing through Greenwich, England, which is also the location of longitude 0. And then you go west from 0 or east from 0 to determine your position on Earth in terms of longitude. Of course, latitude is another deal. You have to take my physical science course to get that. But once that was agreed upon by some committee of the organization, then it was standardized using a platinum iridium bar of a certain shape. And the shape would give it rigidity so that it would not change. Now, since then, the standard, the bar, which is probably still in that cave in its own cylinders, has now been standardized in terms of something that can be reproduced anywhere in the universe. So many wavelengths of a laser beam of a particular color. And if you have the right instrumentation, you can produce a standard meter with that device and compare it to anything. So that's length. Time is a standard second. The second was sort of grandfathered in. Since ancient times, we've been using astronomical observations to mark time. And eventually we came to using a second as one of those measures. So what the committee had to do was they had to say, okay, what is a second generally agreed upon by most peoples in the world? And then once they fix that value, that's where it stays. That is a second. And it's reproduced usually with great accuracy by what's known as an atomic clock. What they use is the disintegration of radioactive isotopes of a certain type, and they measure the disintegration with very high precision, very high accuracy, both. And we'll describe what that is later, so that the second can be reproduced at will, as long as you have the equipment to do it. Temperature. The standard unit of temperature is the Kelvin. Well, the Kelvin is strange to most people, but here's the connection. The size of the Kelvin degree, say you have a thermometer. The size of the Kelvin degree, say that's 1K, is exactly the same size as 1 degree Celsius. Okay? The only thing that changes is where does 0 start, right? For the Celsius, 0 starts at the melting point of water, or the freezing point of water, whichever. And then we mark higher temperatures positive and lower temperatures negative. The Kelvin, though, 0 point is absolute 0. So it has no negatives in the expressions. They're all positive numbers. That's the advantage of Kelvin. And we'll talk about temperatures a little more later. Electric current is the ampere. And actually, the ampere has been standardized, but the ampere is actually it's a derived unit, but now it's fundamental because it's been agreed upon and established. But the ampere is so many coulombs passing a point through a conductor each second. But in this class, we're not going to use the ampere, and we're not going to use the second one. We are going to use this one. We're not going to use this one. We are going to use the mole, but I have to define what that is. The mole is simply just a defined number of things. It could be atoms, molecules, it could have a mole of chickens. It doesn't matter. A mole is a mole, and it represents a number of things. So those are the fundamental units. The problem is that the size of things that we measure varies. And maybe it's not convenient to measure something in kilograms. Maybe it's more convenient to measure something in a smaller unit. So we need a multiplier, a modifier for these units in case we want to measure something smaller or larger. We can change the units. Okay, that's what we're going to do next. We're going to look at those prefixes. All right. The purpose of the prefix is to change the size of the unit. So think of the prefix as a multiplier. It can either make the unit bigger or make the unit smaller. depending on what the prefix means in terms of mathematics. So these are some that we use. Let's focus on this one, the kilo. It's represented by a small k, and the small k means times 1,000. So if we put that k in front of any other unit, it means your unit now has been changed to 1,000 times bigger. And let's focus on the kilogram, right? We've got a fundamental unit called the kilogram, but notice that the kilogram has a prefix in it, right? So the kilogram is actually 1,000, excuse me, 1,000 times a gram, okay? The gram has been used for centuries by alchemists and then by chemists and other scientists. But for purposes of standardizing the fundamental unit, the gram is too small. It's very tiny. If we made it out of platinum iridium, it'd only be about that big. Okay. The problem with standardizing something that small is the introduction of error. Every measurement has error. We'll talk about that later also. But for now, if I handle that standard gram with my bare hands, I'm going to put fingerprints on it. And that's going to significantly change the mass of that little piece. So, or if I scratch it, right, that would change it also by a significant percentage. So if we take the gram that we're given from history and we multiply it by 1,000, we get something a lot bigger. And now the imposition of any tarnishing or unforeseen altering of that mass is a very, very small percentage. So we don't want to do that, of course, but if it happens, say in a secondary standard, that a kilogram mass that's based upon the fundamental is going to be knocked around a good bit, then the change in its mass hopefully will not significantly impair its usage in comparing it to other measured masses. Okay, that's why we use the kilogram as our standard, which is actually a derived unit from the gram. All the other measurements, we use prefixes against the fundamental unit itself. So what if we use that mega and we say this one, mega gram. So the megagram is 1,000,000 times. So it's going to be equal to 10 to the 6th times grams. Well, what's that in kilograms though, right? Well, here's the easiest way to do that. 10 to the 6th is what? It's 10 to the 3rd times 10 to the 3rd, right? Right? Everybody's had enough math to know that 10 to the 6th is 10 to the 3rd times 10 to the 3rd, because it's 10 to the 3 plus 3, which is 6, right? And that's times grams, okay? What is this equal to? That's equal to this, 10 to the 3rd, right? So 10 to the 3rd grams here is a kilogram. So this is your K prefix. Actually, let's change that. Let's move it. I think it'll work better. Let's move it over here. This one is your K. And this one is your gram. And this one is 10 to the 3rd. Okay, that's a megagram. So now we know that a kilogram times 1,000 is a mega. Okay. There are other ways to do that, but I thought this would be a convenient way to explain it. All right, let's pick a different unit of measure. Suppose we take a meter. Say we have a meter of something. And we want to use a smaller unit than a meter. A meter is too big, right? So a meter would be, let's see, for argument's sake, let's say that's a meter. If we want a unit that's smaller, say a centimeter, then the centimeter would be 0.01 times a meter is equal to a centimeter. So what's 1/100th of a meter? Well, let's see. A tenth would be about like this, and this would be maybe a centimeter. It takes 100 of those to make a meter. Okay, so this chart of prefixes goes smaller. The next chart will go bigger. And you can use any one of these others to change the unit of measure. Notice that if we have, let's take a real number and express it in different units of measure. How about that? Let's say we have 6 meters, right? And we want to express that as centimeters, right? So we need to take a tenth of the meter. Excuse me, 100th of the meter. So 100th of that would be centimeters, and that would be, but how many centimeters are there in a meter? If we have 6 meters, that means we've got 100 centimeters in each one of those meters. So that means we have 600 centimeters. Right? Does that make sense? If you have 6 meters, then you don't want to go 0.06 centimeters. That's too small. That's only down here like that. That doesn't make sense. So 600 centimeters makes more sense. Okay, notice one thing about these two numbers. This unit of measure got smaller, right? Between here and here, it got smaller, right? What happened to the unit? It got larger. So when the unit of measure becomes smaller for the same number, then the value for the number gets bigger. And that works the other direction too. If we went backwards, if we went from here to here, this unit got bigger, so this number gets smaller. That's another way to check yourself, see if you've made the conversion correctly. I'm going to show you a better way. I'm not sure if it's today, but eventually I'll show you a better way to make those conversions where you won't make mistakes. You don't have to do this stuff in your head. Okay, let's look at larger numbers. These others, milli is 1,000th of, micro, this little expression here, that's the Greek letter mu. And we use it to express a millionth. Micro equals 10 to the minus 6, or a millionth times. Nano is 10 to the minus 9th, or a billionth. And everybody knows nano. If you got sportswear on the label, it says, I think it has to say that it's infused with nanofibers. Right? Those fibers are measured on the order of a billionth of a meter. Okay, let's go bigger. Oh, it's not going to go bigger. Okay, we've only given it a million times and 1,000 times. And then we went to smaller. So everything, I'm trying to think if there's going to be a need for any of the other prefixes. Can't think of any right now, not for this class. Okay, so the fundamental unit for the meter, for the length is a meter. A kilometer, kilo means 1,000. So 1,000 times a meter is a kilometer. Okay. And then these other possibilities, you could have, we talked about the centimeter. The decimeter is a tenth of, deci means tenth, centi means 100th, milli means 1,000th, and so forth and so on. Now, volume is not a fundamental unit. Volume is a derived unit based upon length. Okay? So if you have an object that is shaped like a cube, right? And the cube has 1 meter on this side, 1 meter on this side, and 1 meter on this side. So height, length, depth. Then you know that the volume of that object is 1 cubic meter. Okay, that's what this is right here, 1 cubic meter. Well, if we take 1/10 of the dimension here, 1/10 of the dimension here, and 1/10 of the dimension there, that's a decimeter. Deci means a tenth. So a tenth of a meter would be like this. Let's see if I can draw that in there. Okay. Right. So this is right here is a tenth of a meter. And right here is a tenth of a meter. And length, depth, 0.1 meter. So this piece of our volume is 1 cubic decimeter. Well, that's a very convenient size to measure for most things. And it's called the liter. So the liter is a derived unit of the fundamental unit of length. So this 1 decimeter cubed is equal to 1 liter. Okay. The liter's useful for measuring large volumes, like gas cylinders. In everywhere else in the world, they measure the amount of gasoline delivered that you, for your automobile in liters. But in the lab, we usually measure a lot smaller volumes, sometimes large, but mostly small. So we need a smaller unit. So what we use is this times 1,000. Okay. 1,000th of a liter is a milliliter. Well, the milliliter can also be derived from length. All we have to do is go 1/10 again on this object right here, and we get a centimeter, right? A centimeter, this is a decimeter, so a tenth of a decimeter is a centimeter, right? The decimeter is 0.1 meters is a decimeter, and a centimeter is 0.01. So this is 1/10 of that. Okay, this equals 1/10 of a decimeter. So if we use those dimensions on this object, 1/10 of that length in a cube, we get a cubic centimeter. And it Turns out that a cubic centimeter, this is a liter, there are 1,000 of these little cubes in that big object. So 1,000th of a liter is a cubic centimeter. So 1 cubic centimeter is equal to 1 milliliter. And notice I write little m for milli and big L for liter. Okay, and that's what we use most often in the lab, the milliliter. In the medical arena, volumes historically were measured in cubic centimeters, cc's. If you find some old syringes that are still laying around, they'll be marked off in so many cc's usually. Well, the nice thing about it is 1 cc or 1 cubic centimeter is equal to 1 milliliter. So you can now label and mark off your syringes or your other devices in milliliters, and you don't even have to change the position of the markings because 1 cubic centimeter is equal to 1 milliliter. The reason that originally cc's were used is because the milliliter wasn't commonly accepted. Plus, when you print on these medical devices, it's not easy to print superscripts. So instead of cubic centimeters, they opted for cc's. That's easier to print. Okay, so this is just everything that I've explained to you right now. Cubic meter and any of these others are derived units. They're not fundamental. They're based upon fundamental. All right. How about masses? Let's make some room here. Mass is a measurement of the amount of substance. It doesn't matter where you find it in the universe. 1 kilogram on Pluto is 1 kilogram on Earth because it measures an amount of something. And that fundamental unit is the kilogram. Now, in this country, we have an intuition about pounds. So this conversion factor, this equivalence, 1 kilogram equals 2.2046 pounds, is an equivalence because the mass that it represents doesn't change. If this mass is 1 kilogram, then it also exerts a force in Earth's gravity of 2.2046 pounds. Now, the problem with this expression is you're conflating mass with weight. Right? Weight is a force, and forces are dependent upon the gravitational field in which you find the mass. But as long as you're on the surface of the Earth, these two are equivalent. I won't go into an explanation of what force. In this course, we don't need to know yet the metric expression of force. I'll just say it, it's a Newton. Obviously, and it's named in honor of Isaac Newton because it's based upon one of his laws. Okay, let's get back to this. But you can use that equivalence to make a conversion, and I'll show you how to do it as soon as we're finished talking about these units of measure. You can go the other direction. Say 1 pound is equal to 453.59 grams. Those are equivalent because the mass is the same. Right? It's this mass, it's worth that many grams, and it exerts a force of 1 pound at the surface of the Earth. Which one of these does not make sense? A gallon of milk is equal to about 4 liters of milk. Does that make sense? Well, you have to have an intuition for what a gallon is. A gallon is equal to 3.8 liters. So it is, yeah, it's about 4 liters of milk. Now, how do I know that? Not because I'm a scientist, but because I read labels. When I go in the grocery store, I read labels. And now everything has a measure on it in the grocery store is expressed in terms of the imperial or the English system and in the metric system on that same package. I think that by law. So if you pick up a bottle of milk, it's a gallon of milk, and look on the side, it'll say 3.8 liters. In fact, some products that we buy have already made the conversion to metric, right? A 2-liter bottle of pop. We all know what that is. It's about that big and about that big around. That's 2 liters. We don't care what it is in the English system because we know what a 2-liter bottle looks like. How about a 200-pound man has a mass of 90 kilograms? That's me. I'm about 200 pounds. So if 2.2 pounds is equal to 1 kilogram, then yeah, that makes sense. Right? The unit of measure has changed, and the number changes also based upon that equivalence. A basketball player has a height of 7 meters. How much is a meter? Well, it's a little bigger than a yard. Right? A yard is 36 inches, and a meter is 39.96, I think, inches. So a meter is a little bit taller than a yard. So if your football player is 7 meters, he's about 7.5 yards tall. He's about 23 feet, right? That doesn't make any sense. A nickel is 6.5 centimeters thick. What's a centimeter? Well, a centimeter is about like this, from here to maybe here. 6.5 of those would be like here to here, right? So is that our nickel? No. That doesn't make any sense at all. Those are counterintuitive, right? Those are wrong. All right. Now to the topic of uncertainty. I mentioned uncertainty when we were talking about the gram versus the kilogram. Every time a measurement is made, there is uncertainty. You never know that what your measurement is exactly what the object represents. So we have to account for that uncertainty somehow, right? We can't get rid of it. It's always there. So we just have to account for it somehow and learn how to manage it. When we write a number, as scientists, we write a number. There we go. 35,103. It's understood by every scientist the world over that you're claiming that the digits here, this 10,000 place, 1,000 place, 100 place, and tens place, these are all certain determinations. We're claiming that those, in that measurement, those numbers are certain. They cannot be changed. They represent, they're part of the measurement that we've made and cannot be changed. The last one is always believed to be uncertain. That's our best guess. So when you write a number and it's expressing a measurement that you have made, be sure that the last number is your guess digit. Because everybody else in the universe, all scientists anyway, are going to see it that way. If you put something here like a 0, they're going to say, okay, that's uncertain. Or if you, well, just be sure that the last one is your uncertain digit. Okay. So what does that mean in terms of actual measurements? Well, when we measure something with a device, it's usually marked off somehow with, well, let's use this example, length. Notice these markings represent here, these markings here between 1 and 2 are centimeters. Right? These markings in between there are 10 of them, so those are millimeters. We have said that those millimeters are our certain marks. So anything, if we put an object up against them like this nail against there, and we blow it up so you can see it. So it's going to be 1, 2, and then 2.5. 2.5 centimeters, but we think it lands exactly on the 5. In other words, the 0.5 of a centimeter. If that's the case, then 0.5 is a certain number, right? Because we have a marking for it. So what we need to do to be sure that we don't throw that away as an uncertain value, we need to say 2.50. We think that the uncertain number should be 0 hundredths. Oh, I'm sorry, I measured that wrong. It's excuse me, 2 point, and there's an 8 here. So this is 0.8 and this is 0.9. My mistake. 0.8. And then we're right on the 5 between the 8 and the 9. Okay, there's something wrong with the slide, isn't there? Because we have a marking for this value right here, that 5. So what we need to do is add a 0 so that we don't mistake this one for an uncertain digit. This is the uncertain one. Okay. That slide needs to be fixed, doesn't it? Right? And what we're saying, right, if we write it 2.85, we're saying that the 5 is an uncertain number. But I submit that it's not. It's one of the certain numbers, and we need to add a 0 to be the uncertain one. Okay. So that's the way we express numbers. Now, we need to talk about these two concepts, accuracy versus precision. To express accuracy, we need to know the true value for a number. Right? Good luck. True values are almost impossible to obtain. So we settle on not the true value, but the accepted value. In other words, a large group, preferably, of scientists have settled upon a measurement of something as a true value or an accepted value. So when they say this platinum iridium cylinder is 1 kilogram, they're saying that that's 1.0000. As many zeros as you want. Okay, that is our accepted value for the kilogram. Now, if we take the cylinder that's supposed to be a kilogram and we measure it, it's probably not going to be 1 kilogram because it's not the original. So comparison of our kilogram to the accepted value is a measure of accuracy. How close are we to the original, to the accepted value? Precision is a little easier to manage. You don't need to know the accepted value to measure precision. Precision is, the best term I can think of is grouping, right? How close, we make multiple measurements, 2, 3, 4, 5, 6, however many. And we compare those numbers. And we say, how close are those numbers to each other? How close are they to the average value? That's a measure of precision. And usually we will have a number and we'll say it's our expression of precision is plus or minus 210. So this number is within 35,313 for the high number, or it could be as low as 34,993. Could be between those numbers. That's an expression of our confidence in the precision of the measurement. There's another way to look at this. Sometimes this visual model helps understand the difference between precision and accuracy. And it's a target, right? We're shooting at a target. And let's say we shoot at this target and notice the average of these values is on the bullseye. So as a composite measure of those holes in the target, we have an accurate representation. But they're really spread out, right? They're not grouped together. So it's good accuracy, low precision. It's accurate, but not precise. Okay, let's say we shoot the target and we get this result. The average there is not on the bullseye. So that is not precise. Excuse me. That's not accurate, but it is precise because we have a very, very narrow grouping. What about this one? There you go. That should be accurate and precise. And then there's one that we haven't talked about. This one, right? Where the holes in the target are spread way out and their average isn't on, it's nowhere near the bullseye. That's not precise and that's not accurate. Those are the possibilities. Now, if you're a hunter and you're zeroing in your scope before deer season starts, then you either want this one or this one. Actually, you want a little better grouping, but it doesn't have to be on the bullseye. So if your grouping is close together, that's your starting point. And then you make adjustments in your scope for elevation and windage. And you bring that grouping from here over to here. If this grouping were tighter over here, that would be better. Then you adjust your scope, and now you got both accuracy and precision in your firearm. Okay. Now we've discussed uncertainty. Where do we go from here? Well, eventually you're going to take a number that you know has some uncertainty in it, and you're going to use it in a calculation with one or more other numbers that have their own uncertainty built in. How do you know how much uncertainty that you must express in the answer? That's where significant figures come in. Okay. First, we have to take individual measurements, individual numbers, and say, how many significant figures are in that number? Then we can go to the calculation afterwards. So first we have to learn how to count significant figures, right? First rule, non-zero integers in a number are all significant, right? So this number has 4 significant figures, 3, 4, 5, and 6. The next possibilities, the next 3 possibilities have zeros interjected, and it depends on where the 0 is located as to whether it is significant in that number. Remember, all non-zero numbers are significant. So now we just have to know, what do we do with zeros, right? Because zeros are placeholders. They have to be there. But are they significant for our purposes? Right? The first class of zeros are leading zeros to the left, right? All zeros to the left of non-zero numbers. And there are no more non-zero numbers out there, just zeros to the left. They're not significant. They're not counted as significant. Example, 0.048. And notice that decimal is bracketed. We didn't orphan it. But those zeros to the left are not significant. So this number only has 2 significant figures. Okay, move to the right. Let's say we put a 0 between 2 non-zero numbers. Right? Those are captive zeros. Those captive zeros are significant. So that 0 is significant. It's bounded on both sides by non-zero numbers. It has to be significant. Otherwise, the number changes. Okay? Then let's move to the right. Trailing zeros. You've got 2 types of trailing zeros. One trailing 0 to the right is there with an explicit decimal point. If there is an explicit decimal point in the number and you have zeros to the far right, then all of those zeros are significant. They must be counted. So this number has 4 significant figures. If you don't have an explicit decimal, then the zeros don't count. So this number, 150, has 2 significant figures. Now, what if you meant, when you made the measurement, you meant to say that all of your digits are significant? Then all you have to do is put a decimal there. Now you have 3 significant figures. Now I know what you're thinking. Why isn't that an orphan decimal? It needs a 0 on this side. Well, we have to make a choice. If we put a 0 to the right of that decimal, what does that do? That adds another significant digit, right? We can't do that. I mean, that's claiming a false digit. So we have to leave it that way. And actually, if this number occurs at the end of a sentence, you don't put another decimal out there. You just leave that decimal there, and that stands for the period also. Okay. Now there's one other class of number. It's called the exact number. Exact numbers have infinite significant figures. Okay. Most of those will fall into the category of conversion factors. Those numbers that we use to convert from one unit of measure to another. We treat those as if they have infinite significant figures. 1 inch equals 2.5 centimeters. Those have as many significant figures as you need. So when you do calculations, you can ignore them. You don't have to use the significant figures, right? Infinite. What do you do with infinite? You don't use it. Or in some cases, we have counting numbers. Counting numbers are believed also to be infinite in their significant figures. 9 pencils, for instance, for our example here. Okay. So how about significant figures in scientific notation? When we write this number, 300 with a decimal to the right, that means all three of those are significant. So we have to keep the zeros. So if we write this one, scientific notation, it's equal to 3.00 times 10 squared. What if we have this one? What would it equal? It would be 3 times 10 squared. Right? So when you create scientific notation, you preserve the number of significant digits in the coefficient. This one only has 1, that one only has 1. This one has 2, 3, this one has 3. That's the nice thing about scientific notation. All you have to do is look at the coefficient. You don't have to count all the zeros. That's been taken into account when you write the number. So if we have a number like this, 0.00300, that would be equal to 1, 2, 3, 10 to the minus 3, and this would be 3.00, because these are not significant, and these two are. Because there's an explicit decimal here, those zeros are significant, and we write it this way. Okay. So when we do a calculation, we're going to preserve all of our digits, right? Our calculator will give us just as many as we want. Calculators are not designed, simple calculators are not designed to account for significant digits. They just spit out as many as you tell it in your register. So we've got to know how to round, because we can't keep all those digits legally. So we're going to use the 5 rule. When you need to round the number, you look at the position that needs to be preserved. Say we have a number like this, 13057. And we need to round to this position right here. That means that we look to the right. Only one place. These numbers don't matter. Just this one. That one's 5. So this one is rounded up. 1, 3, 1. And these disappear as zeros, because we have to hold the places, otherwise the number is wrong, right? We wouldn't round this to 131 because that's nowhere near 13,057. Now, if this were less, if this were, say, 4, that, then the rounded number would be 0, 0, 0. Okay? 5 or above, round up. Less than 5, round down. Okay. So, if you encounter a problem on an exam, and it says round this number to blah blah significant figures, then you use your rules to determine where the significant figures are, and then you move you round at the position that will give you the correct number of significant figures. We're going to talk about calculation rules in a second. And in fact, I'm going to leave this rounding rule till later, because this rounding rule, where you carry your calculations all the way to the end, then round, that only works for multiplication and division. If your calculation involves addition or subtraction, then you can't use this rule. So let's go to mathematical operations using significant figures. Here's our example. We've got 2 types of operations: multiply, divide, add, subtract. That's it. You only have two rules, one for multiply, divide, one for add, subtract. Then, of course, if you have a combination calculation where you have add, subtract embedded in multiply, divide, you have to use your rules of operation or parentheses. Well, actually, you do use the rule of operation because the first one is parentheses. And I'll talk about that in just a second. But multiply, divide says that when you get your answer, you can keep all your digits that the calculator gives you, but then you have to decide which one of the multipliers has the least number of significant figures. And that's where you round your final answer. In this case, this one has 2, this one has 4. So our answer, the calculator gives us this answer, and we have to round so that we only have 2 significant figures left. Okay, add, subtract. This involves limiting. We are limited to the number of decimal points based upon the number with the least number of decimal points. Okay, so our example. This first example has 23.445. Notice we've lined up the decimal points. We add them both together and we get this number, but we cannot keep this digit out here because there's nothing there. So we have to round to this position, and that's why the answer is 31.28. We round it up. Okay. Before we go to that, suppose you have two numbers and one of them does not have an explicit decimal point. So let's take this one, 2, 3, 4, 5. Let's just do that, 2, 3, 4, 5, and say this one is 7, 8, 0. We've lined up the understood decimal points right here. So when we add this number together, we would say 5, 2, and 1, and 3. Okay. So that's the number our calculator gives us. Where do we round? This position is not significant, so we would round there. 3, 2, 3, 1, 3, 0. We need a placeholder. That would be the answer. Now, only if this had a decimal, we'd be able to keep all of those digits. Notice one other thing. With add and subtract, if you're asked how many significant figures are in the, multiply, divide. If your calculation is multiply, divide only, and you're asked by an exam question, for instance, ask how many significant figures are in the answer. It's simple. You just find the multiplier with the least number, and that tells you how many are in the answer. But with add and subtract, you can't do that because this one has 2 significant figures like that. This one has 4, and the answer has 3. So when the question is how many significant figures on the answer and the operation is add or subtract, you've got to do the calculation to determine the answer to the question. All right, now, as a practical matter, you have 2 graduated cylinders here, right? Notice this one is marked off in milliliters here and 2/10 of milliliter markings in between. This one is marked off in tenths of a milliliter and 200ths milliliter marked in between, right? So which one will give you the most accurate measurement of any measurement that you make? The one on the right. But if you combine the values, if you combine these two volumes together, what can you claim? The least accurate device determines the accuracy of the overall measurement. Right here, that. So, if we add these together, 2.8 and 0.28, we can only claim 3.1 as our total volume. And that's the add subtract rule. I'm not going to go into details right now. The limited precision is based upon, as the limited accuracy too, is based upon the least accurate device in the chain. Okay. Now, remember, think back earlier when we were talking about unit conversions, and we were sort of doing them in our heads, like centimeters, decimeters, or whatever the case may be. This is the way that you can do unit conversions without making mistakes, right? Without having a brain fart and putting the wrong answer down. It's called dimensional analysis. And the heart of a dimensional analysis is the conversion factor. So you obtain the conversion factor as an equivalence. So many feet, let's see, 1 foot equals 12 inches. That's an equivalence. Or 2.54 centimeters equals 1 inch. That's an equivalence. And we use that to make a conversion factor. And then the conversion factor can be used to convert between those two units that are in the factor itself. I'll show you how that works in just a second. You need the equivalence statement. Yes. You choose the arrangement of the equivalence statement that will give you the answer. Now, I'm just going to run through these and show you. It'll make more sense when I show you how to do it. Then you multiply the quantity by the conversion factor. You cancel units. If one unit is in the numerator and the same unit is in the denominator in the chain of conversions, they cancel. And then check to see that you have the right significant figures. Okay, so let's say we have a golfer puts a ball 6.8 feet across a green. How many inches does this represent? Okay, we're given 6.8 feet. Okay, we want to know how many inches is that. All right, we need a conversion factor, something we can multiply by that number that will give us inches. Okay, so our equivalence is 1 foot equals 12 inches. Okay, that's our equivalence. So how does that become part of the calculation? Well, remember, you can do that to any number. Any number times 1 is itself. You can multiply any number times 1 and you violated no mathematical rules. Okay, so what if we divide both sides of this equation by 1 foot? Right? That's another mathematical rule. If you divide both sides of the equation by the same factor, or you multiply both sides by the same factor, then the equation is still valid, right? So this side still equals that side. But notice this side, a number divided by itself and its units is equal to 1. Right? So this expression here is equal to 1. We can substitute it in there. All right, so let's do that. 12 inches divided by 1 foot is equal to 1. There we go. Notice this number, remember, any number written without an explicit denominator is the numerator. So this is always like that. That is in the numerator. This is in the denominator. When you multiply those together, that one cancels that one. And you're left with these units of inches, just as we wanted. So 12 times 6.8 is what? There it is. (82 inches). Okay. Now remember what I said earlier. Exact numbers have infinite significant figures. So we don't have to deal with this one. We only have to look at that one. It has two significant figures. Two significant figures, two significant figures. We're good. Notice something else before we move on. If this is equal to 1, right? 12 inches divided by 1 foot. If that's equal to 1, then this is equal to 1. Right? Right? If this is equal to 1, then flipping it doesn't change anything. It's still equal to 1. So that allows us, if we have inches here and we want to go to feet, all we have to do is flip the conversion factor. It's still equal to 1. And now the inches cancel and leave us with feet. Okay. This example is in here to emphasize the fact that you may not have a single conversion factor that will get you where you want to be in the units for your answer. But that's not a problem. It just takes more than one conversion factor. You can chain them together as long as the units cancel and in the end leave you with the desired unit, and each conversion factor is equal to 1, then the starting number times 1 times 1 times 1 times 1 is okay. Each conversion factor you stick in there is designed from an equivalence to cancel the units you don't want, keep the units you do want. So in this case, we know we've got 4.5 pounds, and we want to convert to kilograms first because we have another conversion factor that will go from kilograms to pounds. That will go from kilograms to grams. So this takes us to kilograms. And this one cancels the kilograms and takes us to grams. And there is expressed in scientific notation. And all we have to look at is this one for significant figures. 3 significant figures, 3 significant figures. We're good, as long as the calculation was done correctly. Now, when you set up the problem like this, that's what I call the thinking part of the problem solution. The rest is number crunching. So if you set it up right, and you know how to operate your calculator, and then you know what to do with the answer, no problem. All right. Let's see here. Let me take just a second to check my hard copy and see how much more we have to cover. Okay, we should be good. What data would you need to estimate how much money is required for you to travel from, in this case, from New York to Los Angeles? What do you need to know? Well, you need to know how far it is, correct? You need to know how many gallons of gas you need. So that means you need a conversion factor for distance to gallons. What is that? Mileage, gas mileage for your car. And then once you know how many gallons, you need to know how much those gallons are going to cost. So that's the price of gas. What does it cost per gallon? And that will give you how much money you need to operate your vehicle from New York to Los Angeles. What if you want to come home? Well, if it's a round trip, you just multiply it by 2. And then, of course, if you're going to do any driving around when you get down there, you buffer, you pad your wallet with a little extra, maybe 10%. And let's see, if you're going to Los Angeles, better make it 20%. It's a big town, a lot of driving, and a lot of stop and go traffic. Okay. So the distance from New York to Los Angeles is about 2,500 miles. The average gas mileage for your car, let's say it's 25, just for argument's sake. Right? It varies all over the place. And the average cost of a gallon of gas is $3.25. That's pretty close to what it is today, but it might vary on your trip on the way down there. So what you need to do is go to AAA or go to, let's see, what's that other app? I forget the name of it, but you can check gas prices on the journey down there and find out, all right, we either want an average, or we want a median, or we want the highest one, just to be sure we have enough money. And you plug that in instead of 3.25. How do those go together? Well, we have an equivalence here for miles per gallon. And notice miles per gallon is equal to 1. So you can flip it, gallons per mile. 1 gallon for 25 miles works because we need to cancel the miles, right? Oops. I thought I had an animation in there, sorry. So that leaves us with gallons, and then this one converts from gallons to dollars. So $325 to get down there, $650 to get back, and maybe $50 to drive around when you're down there. All right. How about temperature? We're going to use temperature as to kill 2 birds with 1 stone. We're going to discuss temperature and then how do you convert from one system to the other. Well, the key fact to remember is that when you measure temperature of, say, I don't know, body temperature, say, you stick a thermometer in your mouth. If it's calibrated for degrees Fahrenheit, it'll give you a value like 97 or 98.6, which is nominally normal. Or if you have a fever, it might be 101 or 102, 103 degrees Fahrenheit. What if you stick a thermometer in your mouth that's calibrated for Celsius? Like you're traveling through Europe and you get sick and you stop at a hospital to get treated. Well, they're going to measure your temperature in Fahrenheit, in Celsius. Well, if you have that same temperature over there as you do here, or you use 2 different thermometers, 1 Fahrenheit and 1 Celsius, what's the difference? Your body temperature didn't change, but the units of measure did change. Aha. So it's valid to convert from one to the other. There's some type of equivalence in there that will do the conversion. So we have to know about the systems first. How are they set up? Well, the first system that came online was Fahrenheit. And that's the name of the man that invented the thing. He was interested in biological systems. So he wanted a range of temperatures in his thermometer that were more closely associated with living systems. So most living systems are in the neighborhood of say around 100 degrees Fahrenheit. See, he set 100 degrees Fahrenheit as a reference point. And then he set 0 degrees Fahrenheit as the coldest temperature he could manufacture. Distilled water and ice manufactured from distilled water. That brought him to 0 degrees. And then he fixed other temperatures to help nail down his system. The boiling point of water under those conditions is 212 degrees Fahrenheit. And the freezing point of water is 32 degrees Fahrenheit. So he had basically 3 good fixed points to set up his measurement. And then he subdivided them in such a way that there was enough space between them so that it could be easily read on a thermometer. So now he had a unit of measure that was 1 Fahrenheit degree, and he had fixed points. Well, what do those fixed points associate to other systems like Celsius? Celsius came along not too long after Fahrenheit and said, I'm not a biologist, I'm a chemist. So, or I'm a physical scientist. So Celsius said, I'm going to pick my 0 point as the freezing point of water. You know, anybody in the world can establish distilled water freezing point and calibrate their thermometers easily. And then that fixes the 0 point. The 100 point is going to be the boiling point of distilled water, right? At 1 atmosphere pressure. So now he had those fixed points and he subdivided them into 100 units. And it's turned out the degree mark in Celsius is bigger than the degree mark in Fahrenheit. So it takes 1.8 Celsius degrees, excuse me, Celsius degrees to equal, excuse me, that's not right. Fahrenheit degrees to equal 1 Celsius degree. All right. So we know the relationship of the degree marks. And we also know that the 0 point position moved. So the 0 point of the Celsius system is 0. And the freezing point of water in the Fahrenheit system is 32 degrees. So put those together and you get this expression. I'm sorry, I had it right the first time. Fahrenheit is equal to 9/5 Celsius plus 32. This accounts for the shift of the 0 point. This accounts for the size of the degree measurement. Because 1.8 times Celsius is equal to how many Fahrenheit degrees are in that interval. Okay, so now that we know the conversion, if we know Celsius, we plug in the value here and do the calculation, we get Fahrenheit. If we know Fahrenheit, we plug it in here, rearrange the equation, and solve for Celsius. Remember, if you have an algebraic expression, an equation, and there's only one unknown, you can always solve for it. Okay? Now, the other system is Kelvin. Lord Kelvin was an accomplished physical scientist. In fact, he did a lot of work in thermodynamics based upon some other rather smart people. Sadie Carnot was one of them. But he noticed that these temperature systems were inherently plagued with one type of error. They had available negative values of temperature. And you can't put a negative value of temperature into a thermodynamic calculation and expect to get a correct answer. He needed a system that had only positive values. So here's what he did. He based, well, this is an oversimplification, right? His published papers, research papers, make a much better argument for it. But for simplicity's sake, I'm going to use this argument. If we have a gas, any gas, and we measure its volume against its temperature. Actually, I'm describing Charles' law for you. We'll get to that later in a later chapter. But as the temperature goes up, the volume goes up. And it goes up in a linear fashion, like that. Okay? But if you make the gas cold enough, it's going to condense, right? Turn into a liquid, and then all bets are off. Right? You can't go any further with it. Speaking of it in terms of gases, but Kelvin reasoned that for the ideal gas, it's always a gas. And he extrapolated the line down to this point. What does that mean? At this temperature, the volume of the gas goes to zero, right? 0, 0 is the origin here. So at this temperature, on the Celsius system, this temperature is minus 273.15 degrees Celsius. It said, okay, that's my starting point. My new system is going to start there with 0. So on a different scale against the volume, now this is 0 K. And we never say 0 degrees K. It's just 0 K. Now everything on this side is positive value. Well, at this point, right, we've moved 273.15. So this is 273.15 K is 0. Now, for our calculation purposes, we're going to drop the decimals off the end. We're just going to use 273. So in order to make the conversion, if I want to know Kelvin from Celsius, Kelvin equals Celsius plus 273. Right? So Celsius at this point is 0, but if we add 273 to it, we get Kelvin. Okay. So now we have our 3 systems of measurement. Fahrenheit and Celsius are anchored in the real world, and Kelvin is anchored in the imaginary world where the gas gets so cold it drops to a volume of 0. But that's not bad because it has its uses in calculations, and those will become obvious at some point in the future in this course. All right. That's how you convert between the scales. Now, what if you're given a problem in which says so many degrees Fahrenheit and the answer is in Kelvin? Well, you've got to do 2 conversions. You've got to convert the Fahrenheit to Celsius and then the Celsius to Kelvin. I suppose mathematical wisdom, I mean, if you know algebra, you could combine the 2 equations. That's possible. And this should do 1 calculation. But we're not going to do that here. Just do the separate calculations and you'll be safe. If you want to know the derivation of this equation, right? 1.8 is the same as 9 divided by 5. Right? I memorized it decades ago as 9/5 times C. But 1.8 is exactly the same. If you want to know how that's derived, here's your website. Has an excellent description of how the equation was derived. Okay. Normal body temperature of a dog is 102 degrees. What is that in Kelvin? Right? Here's where you're going to have to convert twice. Oh, it's not going to show us, is it? Okay, so you would take 102, convert it to Celsius, then add 273, and you will get, I'm sorry, I didn't know I had animation on this one. So there's our conversion to Celsius. 39 degrees Celsius is 102 degrees Fahrenheit. Add 273, 312 degrees. By the way, if 98.6 is the accepted value for standard normal body temperature for a human, an adult human, 98.6 degrees Fahrenheit, what is that in Celsius? You can do the calculation or you can memorize it like I have. It's exactly 37 degrees Celsius is normal body temperature. Okay. Here's another interesting problem. You've got two different systems, and there's an equation that converts between the two. But the interesting question is there a value in each system, like so many degrees Celsius, is exactly equal to the same number of degrees in Fahrenheit? How would you answer that question? Well, you take the equation first and say, well, if they're both equal, then you can use a variable in both cases for degrees C and degrees Fahrenheit. Just make them X and then solve for that one unknown. Right? So that's what I've done right here. Substitute X in that equation and solve for X. And when you do, you find out that minus 40 degrees Celsius is exactly the same temperature as minus 40 degrees Fahrenheit. Okay. Now, I don't know if any of you have experienced minus 40 degrees Fahrenheit, say at some place in the country, up in the mountains of the Rocky Mountains, or let's see, what's the coldest place? It's International Falls, Minnesota, I think, is the coldest place in the lower 48. You might be able to feel minus 40 degrees Fahrenheit. Well, I know what minus 40 degrees Fahrenheit feels like. In my youth, as a student, I was working part-time at a hotel and restaurant supply, right? We supplied hotels and restaurants with food products and other products like napkins and plates and whatever. Well, we had this freezer that was set at minus 40 degrees Fahrenheit. We called it our blast freezer. If you put hamburgers on a tray in there, within about 10 minutes, they're frozen solid. Well, the reason I know how that feels is once a month, the company had to do an inventory of all their products. So we came in early, like 3 o'clock in the morning. They fed us a high-calorie breakfast of sausages, bacon, eggs, biscuits, and butter, whatever we wanted. And then we put on our insulated coats, hats, gloves, our clipboards, and we went to work. Well, I was a part-time employee, low man on the totem pole. So I was elected to go inventory the blast furnace. So I would go into the blast furnace, and after about 10, 15 minutes, I had enough. I'd come out into the cooler and warm up and then go back in. And I keep doing that until I got the job done. But I knew it was very cold. Excuse me. All right. So we're going to discuss density and use this to introduce the concept of equations, solving equations, and what equations mean. So we define density as the mass of a substance per unit volume. Okay? In mathematical terms, the variable density is equal to the variable mass divided by the variable volume for that mass. So D equals mV. That's an algebraic expression. How do we know that the common units are what's reported here? Well, if the mass is in grams and the volume is in milliliters, then any number that we have in here, say X and Y, whatever that calculation is, we have Z grams per milliliter. Remember, if the units don't cancel, you have to keep them in the answer. So grams per milliliter is the unit of measure for density. In this case, well, what if instead of milliliters, we prefer to use cubic centimeters? And remember, On a dimensional scale, cubic centimeters and milliliters are exactly the same. So it's just a reporting preference. If we get that Z number in this calculation, the units of measure are equivalent. Grams per milliliter, grams per cubic centimeter, exactly the same. Only by convention, this density unit is usually for liquids. And this unit of measure is usually for solids. How about gases? Gases are less dense, right? So we need more of them to make a measurable weight. So we usually report gases as grams per liter. Okay. All right. So there's our equation. And before we get to this, if you have two values in this equation, you can solve for the third one because we have three unknowns, right? We have three variables. If we know that one and that one, we can calculate this one. If we know this one and that one, we can solve for this one. Or if we have this one and that one, we can solve for that one. It's like I said earlier, if you have an equation and you've got numbers for all the variables except for one, that's your unknown, you can solve for it. All right, so in this slide, we're making the point of the difference between regular shapes and irregular shapes. If you know a regular shape and you measure its mass, put it on a balance, measure its mass, then you can calculate its volume using geometric laws, formulas, right? If it's a sphere, right, we know that the volume is equal to 4/3 pi r cubed. So you need to know the radius here. If it's a cube, right, we already know how to do that one. Right, you just measure one of the sides and cube it. But if you have a regular and irregular shape, like a person, how do you determine the volume of that person? Well, one of the simplest ways is by displacement. Right? If you drop something that's that's denser than water into the water, then it will drop to the bottom, and while it's doing that, it will displace a certain amount of water. So if the water in your container is calibrated at a certain volume, then when you throw something into it, the volume will rise. So the volume of the object is the difference between the two. And that's what we're showing here. This woman jumps into the water and she has to be completely submerged, right, to realistically express her volume. But she may have to expel some air, breathe out in order to drop. But when she does that, notice the volume here changed from there to there. That difference is her volume. And we can get her mass easily on a bathroom scale or a more accurate scale in a laboratory setting and determine her density with our formula. Now, the other condition that must be met is if the object you put in the water reacts with the water. You don't want that. If it doesn't react with the water, perfect. All's good. But if you throw something like sodium metal into water, it will instantly react with the generation of a lot of heat, hydrogen gas, and maybe even combustion once the gas reaches the air. So in that case, if we needed to measure the volume of a chunk, irregular shape of sodium, then we would drop it into something that it doesn't react with, like mineral oil. Okay. All right. So I'm coming up on 11 o'clock. I think 11 o'clock is when we're supposed to stop. Be sure. Yeah. Since I'm recording this and there's nobody sitting across from me, I'm going to finish it. But if you come to class and sit in class and 11 o'clock rolls around and I'm not done and you have someplace else you have to go, then you just get up and go. But in this case, everybody appears to be taking this course on the web. So you just watch the video until it's over. So what's the density of this object? 17 grams of this mineral has a volume of 2.35 cubic centimeters. So all you have to do is use the formula, plug in the values, and determine the density as 7.57 grams per cubic centimeter. Notice, let me make a point here. There's a difference between an extrinsic value and an intrinsic value. Intrinsic value. Sometimes this is called capacity, and this is called intensity. Okay, what's the difference? An extrinsic property changes the value with the amount of substance. So mass would change with the amount of substance, right? So it's an extrinsic property. Mass is an extrinsic property. Volume is an extrinsic property, right? An intrinsic property or an intensity factor doesn't change with how much substance you have. So if I have a brick of gold, it's going to have a certain density of so many grams per cubic centimeter. If I have a gold coin that's pure, it will have the same density, right? It doesn't matter how much you have. The intrinsic property is the same. And most of the time, the intrinsic properties are ratios, right? Like mass per volume or others like it. They're ratios. There is one important one where the intrinsic property only has one unit of measure, and that's temperature. The temperature of a ball that it's at 30 degrees Celsius is the same as a ball this big at 30 degrees Celsius. It doesn't matter the size, it's the same temperature. Okay. How about what's the mass of 49.6 milliliters of a liquid? Well, we know the density at 0.85 grams per milliliter. Well, you got your formula. Which is the answer you want to know? What is the question? What is the mass? So solve the equation for mass. Or plug in your values and then solve it for mass, like we did here. Okay? 42 grams. How about an object that has a mass of 243.8 grams and occupies a volume of 0.125 liters? What's the density of this object? Well, notice that the units of the answer are not the same as the units of the calculation, right? The volume is in liters. So you've got to convert liters to cubic centimeters, okay? 0.1125 liters is how many milliliters? Okay. Well, we need to move the decimal place to the right. 125 milliliters. How do I know that? Well, I know that because I've been doing it for decades. But we can prove it if we use dimensional analysis, right? We want to cancel liters and leave us with milliliters. Now what we have to say is how many milliliters are in a liter? That's our equivalence. Well, there are 1,000 milliliters in a liter. So the liters cancel. 0.125 times 10 to the third, or 1,000, moves the decimal place, 1, 2, 3. There's your answer. Okay? But we're not done yet because we need cubic centimeters. But that's easy. Milliliters are cubic centimeters. So 125 cubic centimeters is the volume expression. And we've done both calculations here in a single pass. All right, there you go. 125 cubic centimeters is the volume, and then we plug it into our formula, and we get 1.95 grams per cubic centimeter. Okay. So, interesting question. Will this object sink or float in water? Right? That depends on Archimedes' principle. This density is almost twice as much as water. Water is 1 gram per cubic centimeter, give or take. So if we throw this thing into water, it will sink like a rock. It may be a rock, we don't know. But if the density is less than 1, then the object will float. Okay. Let me see. Yes, this is the last slide. So we're done with this one. Copper has a density of 8.96 grams per cubic centimeter. That's definitely more than water. If 75 grams of copper is added to 50 milliliters of water in a graduated cylinder, to what volume reading will the water level in the cylinder rise? Okay, this is a more complex problem. Sometimes it helps to draw pictures. So let's draw a picture. Graduated cylinder, right? Like that. Okay, and it's got markings on it, right? Volumes. And 75 grams of copper is added to 50 milliliters of water. So let's say we have 50 milliliters of water already in here. That's right. 50 milliliters of water. Okay, that's where we start. And we're going to take copper, this copper object, and drop it in there. And we want to know what's the new volume. Okay, well, the new volume, X milliliters, is how is it determined? Well, if we drop the copper in here, right? If we drop that copper in here, the volume is going to move up. How much is it going to move up? It's going to move up by 50 plus the volume of the copper. And that's equal to the X milliliters, the final volume. That's how we add that much volume to this, and it equals that value. Okay. So we need to find out what's the volume of the copper. Okay. So here's our formula. We're going to solve it for volume. And then we're going to substitute in values. 8.96 grams per cubic centimeter. And remember, cubic centimeters and milliliters are the same. So we can just as easily say this, milliliters. But what's the mass? 75 grams. Okay, that's the volume of the copper. Okay, so let's do that calculation. Get out your calculator and say 75 divided by 8.96. And that's 8.3, my calculator says 8.3705. Right? This is an add subtract rule. We're going to put it into this is a multiply divide rule. We're going to put it into an add subtract rule, so we have to determine the number of significant figures before we go that far. Notice that what we have here is grams to cancels grams and leaves us with milliliters. Okay, this is 3 significant figures, 3, so I have to use 8.37 milliliters. Now, if I put it into this calculation, 8.37. Now we're going to have to, let's do it this way. 8.37. So we get 7,385. Okay. We can only use that many positions. So this has to be rounded up to 4 milliliters. 58.4 milliliters. We're looking for volume, right? So we solve for volume. That's the volume of the copper, but that's not the final answer. That's how much the water moved. The final answer is what is the value of the final volume. So we add them together, 58.4 is the final volume. So this is an example of a problem that is complicated and has to be broken down into smaller pieces, right? We break it down into a small piece to find the volume movement of the water, and then to find the final answer, we take that movement and add it to the original, and that gives us our answer. Okay, I think that's it. Yep, that's it for chapter 2. And let's see, next Tuesday, we'll talk about the concept of matter. What does it matter? Matter. Anything that occupies space and has mass, that's matter. All right, we'll start that one next Tuesday.